before I explain the fundamental variable theory, I need to make sure you understand superposition in quantum mechanics. I will end this first explanation by summarizing the theory of superposition. Quantum objects are described as either a particle or a wave. When a quantum object is isolated, meaning, when it is not disturbed, it exists in its wave form. In this wave form, we cannot know the orientation or position of the quantum object unless we measure it. But, the moment we place the wave under measurement, it will collapse into its particle form. It is in this particle form alone that we can tell the position, or orientation of the quantum object. This is in part why superposition is only associated with waves. Let me prove this. For this demonstration, let's start by examining an electron in its particle form. Here is an electron particle. By looking at this electron particle, I'm sure you can tell the orientation is in a spin-up state. Here is the same electron particle after 5 minutes. By looking at this electron particle, I'm sure you can tell the orientation is in a spin-down state. Again, here is the same electron particle. By looking at this electron particle, I'm sure you can tell it is located at point B. Now, let's look at this same electron in its wave form, and see if you can answer some simple question about the state of the electron. Here is the same electron in its wave form. By looking at this electron wave, what is the orientation of this electron? I'll give you a second to think about it. Okay, maybe that question is too difficult. Let's try another question. What is the position of this electron wave? By merely looking, if you claim this electron is in a spin-up state, what you will be asserting is that the electron is not in a spin-down state. Likewise, by merely looking, if you claim this electron is in a spin-down state, what you will be asserting is that the electron is not in a spin-up state. Obviously, because we cannot claim that the electron wave is in any of these two states, the best way to describe the spin orientation of this electron wave is to say, the spin orientation is in a state of superposition. Meaning the spin orientation exists in all possible states. Likewise, because we cannot claim that the electron is located at a specific point, the best way to describe the position of this electron wave is to say, the position is in a state of superposition. Meaning, the electron is located at every possible point. This is what Schrödinger was trying to explain with his thought experiment, when he implied the best way to describe the state of a cat inside a poisonous box is to assume the cat is dead and alive at the same time. If you compare this electron wave to the Schrödinger's cat inside a poisonous box, superposition of spin orientation will become clear to you. To know the position or orientation of this wave, we need to measure it. But, the moment we place the electron wave under measurement, it snaps into its particle form. Only in this particle form can we be certain of the position or orientation of the electron. Measurement is similar to saying, only when we look inside the box can we tell if the cat is dead or alive. Therefore, what superposition means in theory is this: until we measure the electron wave have all possible spin orientations simultaneously, or that the electron wave doesn't have a spin orientation. Likewise, for the position, it means, the electron wave exists in all possible position, or that the electron is not located at any of the point. In 1935, the argument between Albert Einstein and Niels Bohr was about the existence of the spin orientation of a quantum object when the quantum object is in its wave form. This is what prompted Albert Einstein to ask Abraham Pius, "Do you really believe the moon is not there when you are not looking at it?" He was referring to the spin orientation of a wave. And if you look at this wave, you will notice that the question makes sense. In quantum mechanics, measurement is often referred to as looking. Now that we've simplified superposition, let's move on to the fundamental variable theory. In this segment, I will prove that there's a difference between spin angular momentum and spin orientation. As we continue, I need you to take note of the three summarized theories of superposition below. These two theories are true for any attribute or state of a system that is described with superposition. Conservation is a well-known theory in physics. It simply states that within an isolated system, an attribute that is conserved stays the same over time unless it is influenced by external force. For example, assume that the momentum of this blue planet is moving at a speed of 5.2 meters per second. The law of conservation of momentum says, the speed and direction of this blue planet will remain unchanged unless the planet is disturbed by external forces. Another example, here is an astronaut called Paul. If the mass of Paul is 100 pounds, the law of conservation of mass says, regardless of whether Paul is on Earth, Moon, or Mars, unless Paul add or remove from his mass, the mass of Paul will remain unchanged. A fundamental attribute of a system is any part of the system that cannot be removed without destroying the system. For example, the electric charge of an electron is a fundamental attribute, in that, even in theory, it cannot be separated from the electron without destroying the electron. Energy is a fundamental attribute of any matter, in that, even in theory, you cannot remove every single energy in a matter without destroying the matter. Lastly, magnetic field is a fundamental attribute of a photon, in that, even in theory, you cannot remove magnetic field from a photon without destroying the photon. Now, in order to prove the fundamental variable theory, we shall apply these three theories we just discussed to different things and see which one is compatible and which one is not. Let's use Paul as our first example. This is the weight of Paul on Earth. This is what Paul weighs when he is on the moon. And this is what Paul weighs when he is in space. Here is Paul again on a strange planet. Let's ask ourselves, what is the weight of Paul on this planet? Because we don't know the weight of Paul until we measure it, we can apply the theory of superposition to the weight of Paul by saying, Paul weighs 100 pounds, 20 pounds, or any pounds possible simultaneously. Or, that Paul doesn't have any weight at all. However, because the theory of superposition applies to the weight of Paul, that alone let us know that weight is not fundamental. Also that weight is not conserved. Again, here is the mass of Paul on Earth. Here is the mass of Paul on the moon. And lastly, here is the mass of Paul in space. Here is Paul again on a strange planet. Let's ask ourselves, what is the mass of Paul on this strange planet? First of all, mass is an inseparable attribute of a matter. That alone let us know that the theory of superposition cannot apply to mass. Secondly, because the mass of Paul remains unchanged throughout different planets in space, we can conclude that the mass of Paul is conserved, and therefore, if we measure it on any planet, we know what the result will produce. This proves that Paul's mass cannot be in a state where, when it is measured, the result will be random. We will use the electron as our last example. Let's begin with an assertion. The mass, electric charge, and spin angular momentum of the electron are fundamental attributes of the electron. Provided this assertion is true, the following argument cannot be false. Now, let's go back to our electron. Here is an electron in its particle form. For this electron to be an electron, regardless of where it is located, or what form it takes on, it must have mass, electric charge, and angular momentum. Obviously, in this case, we don't have to measure the electron to prove spin orientation. We can see that the electron has a spin orientation. An electron particle is often drawn with an arrow showing spin orientation because it is indisputable that when an electron exists as a point particle, we can accurately tell either its location or spin orientation. However, at this point, we can't determine which one of these three theories applies to the attributes of the electron, and which one doesn't. The reason is because the electron can also exist in another form called the wave form. So let's examine the same electron again, but this time, in its wave form. Notice that in this wave form, the spin orientation is not there. In fact, the spin orientation is not compatible with the waveform. I know this is true because, if anyone tries to dispute this assertion, they need measurement. The moment you place this wave under measurement, it will become a point particle. Only when the electron is a point particle can anyone see or tell the spin orientation. Now, you can argue that we can't see the mass, electric charge or the angular momentum when the electron is in its waveform either. And you will be right. What you cannot argue against is that, before measuring the electron, that is, when the electron is in its waveform, the electron doesn't have a specific mass, specific electric charge or a specific angular momentum. These three things are fundamental to the electron. Meaning, even in theory, you cannot separate them from the electron without destroying the electron. Okay, I know what you are thinking. Let's assume you take the argument one step further by saying, I agree that angular momentum is fundamental to the electron, but instead of being specific, couldn't the angular momentum of an electron wave be in a state of superposition? The problem with that argument is this: angular momentum is not only fundamental, it is conserved. Therefore, it is not compatible with this three theory of superposition you are looking at on the screen. Argument 1. Something that is conserved, meaning unchanged, preserved, protect, or maintain, cannot also be in a random state. Randomness is not conserved. In fact, conservation and superposition are incompatible. Argument 2. When an attribute is fundamental to the existence of something, we cannot under any circumstances, even in theory, assume that the attribute doesn't exist in that thing. As a result, because number 2 cannot be true for spin angular momentum, number 1 cannot be true as well. And remember, in theory, you can't accept number 1 without accepting number 2. Spin orientation, on the other hand, is subject to the theory of superposition. Meaning, number 1, number 2, and number 3 are true for the spin orientation of an electron wave. This is how I know there is a difference between spin angular momentum and spin orientation. In summary, spin angular momentum is conserved, spin orientation is not. Spin angular momentum exists in all quantum forms, spin orientation only exists in the particle form of a quantum object. We can assume that spin orientation doesn't exist. I mean, just look at a quantum wave and you will make the same conclusion. However, we cannot under any circumstances assume that spin angular momentum doesn't exist.